Thank you very much. Thank you for the introduction, also for inviting me to give this talk today. Thank you all for coming. I especially appreciate when it's such a hot day. I apologise in advance for the sounds of traffic going past. That's because I've got the windows open, which is absolutely essential. So yeah, I thought, yeah, explain a little bit more. In terms of how I ended up doing what I do and what my job is now at the Melrose. So yeah, my background is in material science and engineering, and I had during my PhD specialised in using X-rays, specifically X-rays formed at a synchrotron, so very bright X-rays to do material characterization. And this then, after I finished my PhD, I went out to a synchrotron in the States, in California. And then an opportunity came up at the University of Kent where they were looking for somebody who had material science and engineering knowledge, also was used to doing synchrotron experiments, and had an interest in the Mary Rose because the University of Kent was partnered with the Mary Rose Trust to do some specific experiments on the wood. So this looked really interesting. I'd started anyway to kind of hear a bit more about heritage science and thinking, oh, actually, you know, these are materials that need looking after. I'm a material scientist. There's a fit there. And so yeah, I applied for the job, got that job at Kent. I actually did take a little turn out of research for a bit, partly because of timing and changing circumstances, and worked for Elsevier for, I only ended up being about 10 months as a publisher and working with social science journals, actually. So it was all quite different. But then the job came up as conservation engineer at the Mary Rose, and I applied for that and got that job. So I started a year before our new museum opened in 2012. And I was tasked then primarily with looking after the ship and getting the ship ready for the drying phase. So it was lots of physical work in, on and around the ship, and liaising with contractors that were working there. Then in 2016, I stepped up to the head of department for conservation and collections care. So this then saw me overseeing the conservation, the collections, so everything to do with the archive. So for every artifact, there's very detailed logs of the excavation, initial reviews of the artifacts of what they were, then conservation treatments, photos. There's a huge archive that goes along with the collection. And also the maintenance. So we were touched on a little bit before that key to the collection is the key to keeping the collection safe a lot of the time is controlling the environment around it. And that takes a lot of equipment to do. So maintenance at the Mary Rose is always then fallen under conservation, because the big, bulky, challenging, expensive parts of maintenance are actually for the collection. And then just this year, I was made deputy CEO. But still broadly, everything to do with looking after the collection. Some other bits have come underneath me now in terms of our curatorial team. But yeah, broadly speaking, it's all bits to do with looking after the collection. And so that, alongside my work inside the trust with my colleagues at the trust, a lot of what I do is partner with universities around the world, actually, depending what we're wanting to do, and work on research projects with them designed to look after the collection. And it's some of those that I was going to highlight today. And this can be looking at trying to understand degradation processes. It could be making new materials. It could be using new analytical techniques, because obviously things are always changing. This is one of the things we find, that we have artifacts that they might have been analysed in the 80s, but obviously the capabilities of what can be done now is very different. So it's a continual kind of cycle round of what more information could we find now. So yeah, usually if I was given a talk in person, I would ask now how many people have been to the museum. I guess the committee could show hands if they've been. So I'm going to assume some of you have and some of you haven't. So just going to give a little bit of the history. So the Mary Rose was a ship of Henry VIII, which he commissioned pretty soon after he came to the throne. One big and common misconception is that she sank on her maiden voyage. So if there's one thing you remember from this talk, she did not sink on her maiden voyage. She sailed for 34 years, really quite a long time, underwent various renovations, the last one being primarily to be able to fit more cannon onto the ship. And this was potentially one of the reasons for her eventually sinking. The ship itself, just go back to that one. So the ship came to a very sudden end in 1545. there was an invading French fleet, which actually was bigger than the Spanish Armada that came later. They had successfully got onto the Isle of Wight, and the Mary Rose, well, this is the most commonly accepted theory. The Mary Rose was going out to confront the invading French fleet. They fired their cannons out of the gun portholes on one side, and then turned quite rapidly in bad weather, and this caused water to come streaming on. So going back to what I said about them putting more and more equipment on, it meant that the waterline had got higher and higher. So there actually wasn't a huge distance from the waterline to the base of the gun port lids. So once they turned and the water was so close to the open gun port lids, the water very rapidly came in. And it was a huge tragedy. Hundreds of people went down with the ship. It wasn't a huge distance off from the coast, from Southsea Castle, but definitely, far enough, and in probability, most of them probably couldn't swim. There were some survivors. I think it's recorded as about 35 survivors who presumably were higher up the ship and got to neighbouring vessels. So there were some initial attempts to try and retrieve the ship, probably with the motivation of some of the expensive cannons and things like that, with very limited success. And then the site remained untouched, we think, until about the 1800s, where the Dean brothers, who were very key in creating what we now call scuba diving gear, they went down, found the ship, and took things from it and sold it because it was fair game. It was an open site. They actually even, I think, set off an explosion at one point to be able to get further into the ship to get to the goodies. And there are some bits that actually have filtered into our collection, which then were excavated by the Dean brothers, went elsewhere, and then they've come back. So there probably are other bits that came from the Mary Rose that are in maybe private collections or other museums around the world. But then it was in the late 60s that Alexander McKee, a local diver and historian, set out with a mission with lots of other people as well to try and find the Mary Rose. And find her they did. And here is some pictures of the excavation. So this is between 1971 and 1982. The photos that I've shown here of the excavations, apparently these are taken on days with good visibility. I don't know if we have any divers in the audience today. I personally have only ever done diving in Egypt, which is very different to this. Very, very clear. You can see, as far as you can. But there's a lot of descriptions of talking about it like, swimming through soup, that normally visibility would be kind of here. And I guess one key point to make here is that all of this has only been possible by lots of people volunteering their time and expertise. Right up until 1979, it was all volunteer based. So the Mary Rose Trust wasn't formed until 1979. So all the work that came before that was just people because they were passionate about finding and excavating the Mary Rose. On the right there is Margaret Rule, who was the lead archaeologist towards the end of that and leading up to the excavation of the ship. She's there looking at some longbows. These, some of you will have seen them in the museum. They are in incredible condition. Everything in our collection survived because the ship went down onto its starboard side, and over years, it's all got covered with sediment. And this is just built up and built up and built up. And what this does eventually is just cut off oxygen to the site or really dramatically reduce it. So if you're looking at an organic material, a piece of wood, normal processes that would degrade that, they just can't operate without oxygen. And equally, corrosion processes, it needs oxygen there. So it just basically sealed everything there. Now, this actually quite perfectly highlights the fact that as soon as you unseal it and you expose it to oxygen, that's when the clock starts ticking and you have to start deciding what you're going to do to stabilize and save them, which is a bit of what I'll show you today. You talked about this earlier. John mentioned this earlier. Some of you will remember this. This is the 11th of October 1982. Next year, it's the 40th anniversary of it being raised. And yeah, so the way that it works is the cradle, which actually is still on now, which is not quite as yellow as that anymore. The cradle was put next to the ship. They actually burrowed underneath it because obviously once it's in the silt, there's quite a lot of suction there. You need to relieve the pressure so it can be lifted. The frame was put over the top and then it was lifted over. The bit, I'm trying to think if I can point this out to you, the bit where it went clank, if you look on the cradle that the ship is on the four corners, there's like these cones. And at the one on the back left, can you see that there's a wire wrapped round? So that's what happened. The wire got in the wrong place. Probably more technical than this, but my kind of crude explanation of it is the wire, and we actually still have that funnel. I mean, here it looks tiny, it is huge, and it's got this whacking great dent in it, and that's what happened. The wire had just got caught around the wrong way, and so it slipped. But it gives you an idea of the kind of force that the stainless steel cone was just slammed in half. Obviously a really exciting time. It was watched by so many people worldwide. There are some things that people were a little bit disappointed because obviously there was only half of the ship. They also had taken off a lot of the decking planks because some of them were a bit loose, so they were meticulously recorded under the sea, and then they were later reunited with the ship. But yeah, that was the ship being raised, which is 40 years ago next October. And alongside the ship, we have over 19,000 artifacts. There is a huge range in terms of the size, the material they're made of, how degraded they are, the purpose of it. One of the things that I love about our collection, and I think makes it quite different to a lot of other collections, is that it's the everyday people's things. So a lot of the time it'll be, you know, the jewels, the kings, the stately homes, and they're wonderful. I'm not saying I don't like those, but there's something about every person on board is represented in our collection. So not only is it the everyday person, but you can see the kind of range of the different statuses within the ship. And also you have objects that we can really identify with. So for example, one of the things I love is this knit comb here that, sure, if you had a knit comb now, it might not be made out of wood, but basically it's the same. You know, it worked 500 years ago, it works now. There's not really been a need to change it. Yes, there's probably extra chemicals and things that are used, but the actual implement is the same. And I love that. And it reminds us that there were people on board that ship, and the whole ethos of the Merrows and the aim of the museum is to try and tell their story. But obviously, key to that is keeping everything stable. So I'm going to talk about a few of the different materials. I was going to start with wood because we have a lot of it. Obviously, it is the material the ship is made out of as well. The ship is predominantly made of oak. That has been determined to be local, probably New Forest oak. This cross section here should have a scale on it. I don't know why it doesn't. It's about that big. And this is very typical of what Merrow's wood looks like, in that inside it looks like you would expect wood to look, and on the outside it's very degraded. And this is because these are the parts that have been exposed to any kind of degradation, potentially before it was covered in silt and the oxygen was cut off. And then what I show on the right here is a light microscope image and then an electron microscope image. And the top ones is exactly how fresh oak would look if you looked at that under a similar microscope. The cells are very full. And what you see below is that some of that material has started to disappear. And that's because it's been eaten away and been degraded. So wood has three main components: lignin, hemicellulose, and cellulose. Cellulose and hemicellulose are essentially sugar, so it just gets eaten. It's an absolute classic one for the bacteria to go for. And with the wood, what happens is when it's underwater, where the wood has been degraded, water fills that void. And so when you first take it out, it looks fine because it's completely swelled with the water. And this can actually be, I've heard, this is quite a common thing with archaeologists, with conservators, that the archaeologists will raise it and be like, oh, that looks amazing. Then it goes through conservation, it doesn't quite look the same. But of course, unless you keep it in water eternally, it's not going to look the same, because whilst it looks perfect, there is some damage that's been done, and we then have to compensate for that. And what we do is we consolidate it. So basically, some of the water is then replaced with a consolidant. In the case of the Merrows, and this is probably one of the most popular techniques, it's an exchange of the water with polyethylene glycol, or PEG. And this essentially is quite a non-offensive, relatively cheap filler. You find it in lots of things. It's in toothpaste and medication and things like that. And if the artifacts are small enough, what we do is we put them, anything that's excavated gets put into a solution, right? So it doesn't dry out. and then you slowly increase the concentration of the peg into the wood. There's calculations you can do based on the density of the wood to work out what's required. There are different grades of peg we can use, so lower molecular chain, shorter chain lengths, they go very deep into the wood, into the cells, and then higher grade pegs will seal the surface of the wood. And again, if they're small enough, what we will then do is put them into a freeze dryer. Now, what this does is you put the items in, you freeze it, so any water that's still left in there will freeze. You then lower the pressure so that you force the ice that's there to sublimate to a gas. And then that gas is then put into a condenser and you collect the ice. Now, what this does is it speeds up the drying process, so it means that you get less dimensional change. So it's a favourable method to use, and it's quicker. So for timbers, it could take anywhere between a month or 3 or 4 months, something like that, if it was a really thick timber. The peg treatment can take kind of 1 or 2 years. These are actually relatively quick to the treatment of the ship, but most treatments in conservation are not very fast because obviously you're trying to slowly introduce something. In the case of the wood, you're trying to slowly introduce something new into it. Now, so with the hull, technically it could have been done, but we would have had to dismantle the whole ship to put it into tanks, or we would have had to build a tank around the ship big enough to fill with peg. There's so many reasons why that would be challenging. The one that I'll say is, and one of the really important things for us is the Mary Rose Trust is a charitable trust. So we get no state funding. Everything we do is reliant on ticket sales and donations. So if we'd gone down either of those routes, it would have been quite hard to display the ship. We wouldn't have been able to get visitors to come. And if we don't get visitors to come, we can't, simply put, we can't keep doing what we're doing. So the idea, the technique used here was to spray the ship. So the picture on the left is showing the ship in the early stages of spraying with peg. The picture on the right is actually one I took just the day before we turned the sprays off, and you can't see very much, but that's kind of what I'm trying to get across. This is what it looked like in there with the sprays off, because it had just got so it was just, the atmosphere was just full of peg. And I mean, I think it was about, the last time I was in there, it was about 30 degrees and about 98% humidity. It was really quite unpleasant to work with. The reason it was quite high temperature is towards the latter stage of the conservation, we were treating with a higher grade peg, which is a solid at room temperature. So you have to heat it to make it a liquid to enable it to get into the wood. So yeah, that was a year before the museum opened. So all of the work around getting the museum ready was also tied in to the conservation, which hopefully we'll be able to see now if this time lapse works. So this was the old museum, the old ship hall, the white building there. This is a camera that was installed in the dockyard taking pictures every so often. You just saw a little bit of snow there. That's really unusual from there. I've lived here 9 years and I think it snowed once that much. And you'll start to see the original structure that was put around the ship get taken back. And during all of this time, the ship was still being sprayed with peg. So it was a really, really challenging project, because you can imagine if you're trying to keep a completely safe, sealed enclosure, and they're also doing construction and walking around with scaffolding poles around it, stuff like that, with the best will in the world, it is a very difficult thing to do. You can also see HMS Victory there. What I love about this as well is you can obviously see the tide going up and down in the background and the current Navy ships. You start to now see the actual building as it is now be constructed around it. But it did involve leaving some of that original building in. So that structure, called the Weem structure, that was put in the 80s, was always thought of as a temporary measure. And I think we took the last bits out in 2016. So it ended up staying there for a little bit longer. I'm just gonna put this along a bit. What you see now is all the compound eventually getting dismantled and getting to the nice arena that we have now. So while a lot of this was happening, we were in the ship hall trying to prepare it for drying. Now, some of this was physically installing some of the bracketing that was needed for the air drying ducts. So you can see on the top right there, these were these tubes that we installed, which then air flowed through to ensure even airflow around the ship. This was all calculated from a model, looking at a scan of the ship and modeling the airflow around it. What we didn't want is for there to be any discrepancies in terms of the temperature, humidity, or the velocity, because that could cause different drying rates. So these were all very carefully placed. So a lot of this we were doing whilst in that murky environment that I showed before, because we didn't want to have the sprays off for too long. So pretty much all the metal infrastructure went in during that other time. And then this is just, as we turn the sprays off, we had some temporary dehumidifiers in so we could just get the ducts in and get it all going. You can then see those ducts inflated. And then at the bottom right, they're the 3 air handling units that feed that environment in the ship hall, and still the ones that feed in there now. And then I've got one other time lapse here. So the next phase of the project, so getting the museum ready and getting ready to turn the sprays off led up to us opening in 2013. We then closed a bit from the end of 2015 to 2016. And that was once the ship was predominantly dry, we were able to change the configuration. So before it had windows and you would look through and there was drying ducts all around the ship. So whilst you got to see the conservation in action, you didn't get very clear views of the ship. So in this, what we were able to do was take down those walls and install floor to ceiling glazing on 2 of them and a balcony on the top. And now this was all a bit hair raising because there is a lot of glass in there and you can see how close those cranes are. There is not a lot of space, partly because of the space of the dock, but also wanting to create the experience of almost like you're walking through the ship. We really narrowed down the space, but it means you want to be very very confident moving the cranes because they could quite easily go into the glass. So you see all of this being put together, and then I think at the end of here it has, this was a PR launch we did where everybody was behind that, and then the flag dropped, and then they were able to see the ship as it is now. And this is how the museum is now. Oh, so on to some of the work. So I said we were busy installing the bracketing for the drying. We were also installing some ways for us to look at how the drying was progressing. And then the other thing we were doing was identifying points where we could take samples from. So these are core samples taken in increment with an incremental borer. So you literally manually drill it in, and then we get out a sample which is about 5 millimeters diameter. The length varies from where it's been taken from, and then we section that and weigh it, and then dry it completely, and then weigh it again, and then you get a moisture content percentage. It's very straightforward, but it's a very effective and cheap and not a big drain on time for us to do, and gave us an indication of how things were progressing. Unfortunately, though, it ended up with a lot of data that is quite complicated because the ship is not uniform. You know, it's degraded to different levels in different parts. So there's different levels of peg in different parts. So there's different levels of water in different parts. So what we worked on recently, I had a student at Imperial College in London who was doing computational methods, looking applied to different materials. So he got in touch with me and said, "Oh, do you have any data that I can work with?" And I was like, yes, I do. So he did some work on this was just kind of averaging across the depth, the moisture content. So these are just some of the key locations. So you can see the different points in time, and he's coded it as well for the time 0 to be dark blue when it was the wettest. So you can see the moisture content on the side. So you can see here the kind of differences from one point to another. Yes, broadly it all moves down, but it's not all exactly the same. Sometimes you might even see that it jumps up a bit, and that's because you've never taken the same sample. You take a sample, then that's destroyed. So then you can take a sample near to it. So while we've said it's a similar location, it's not the exact same sample because you can't put it back once you've dried it out. But it has given us some good data. So he then went away and worked on this data. This kind of shows you then all the different depths into the wood. So 0 millimeters being the surface of it, all the way down into the wood. So he plotted the average moisture content against the days for the different depths to start off with, from different points on one side of the ship. He then applied various equations to that to smooth it out, to get rates of what was happening. And then from that was able to build this model where you've got the depth of the wood. So this is the surface of the wood. It's got the days will tick by there, and a color code of the darker the blue is, the wetter it is. And what you can see as it progresses, you see this drying front come into the wood as over time that moisture is lost. You certainly see some differences as well, where you will get fronts moving through the wood as it dries. So yeah, that's been really helpful to try and find a way for us to visualize the drying and understand what's happened. The ship is pretty much dry now. We stopped taking samples because the wood is in actually such good condition that it's very hard now to manually take a sample. It gets very hot, so obviously it'll burn off the water, and also the force that you have to use to take it, you lose any meaning with the depth because it can end up getting a bit squashed. But we got some really interesting information from that. We also then, whilst we were preparing for drying, we installed some targets around the ship. So these are these little prisms. And then we have a total station, which is in the center of the ship. And what this does is 3 times a day, it shines a laser. It finds reference points, which are attached to the cradle. And then it finds these points around the ship. And what it gives me is these 3 coordinates. So it's a very handy tool for us seeing how things have moved over time. And one of the ways that we've then looked at this is then by taking the different points and then putting a scale down. Please do note the scale on the side here. That's not compared to the picture relatively how much it's moved. That would be very worrying. But you can see, interesting trends in here. Obviously, everything is moved down. The ship is on a cradle, and then as you dry it, it is just going to go into the cradle like this. But you see other interesting trends of on one deck along the length of the ship, there being some movement this way and then some movement the other way, the deck above. This is all to do with what supports are there. And most of the time, yeah, it's going down and inwards like this. And this is probably mostly to do with its positioning on the cradle as it rests into the position once the residual water has been removed. So that gives us an indication of specific points on the ship. This here is just, and that one of the points is an example showing you the kind of amount of movement and the difference in the 3 different directions, again with height being the main offender of the most movement. One thing this did do was inform us of some bits that were moving that were a potential worry. Particularly, there were some deck beams that you could tell from the movement of the total station that they were twisting. So because we only have half, actually more like a third of the ship, because we don't have the castles either end too, we, compared to some other projects, from a mechanical stability side, are in a slightly better condition because we don't have as much weight. One of the difficult things for shipwrecks when they're put on display is they were never designed to be out of the water. They're designed to be in the water and for the water to take the pressure. So it's incredibly difficult to display them whilst properly supporting them, because if you were properly supporting them, it would be completely covered all the way around, but then you wouldn't be able to see anything. So this is quite a key thing for us, of having the balance between what's going to preserve it, but what's going to allow people to come and enjoy it. But what we do have, as we have half the ship, is you've got deck beams that would have been attached to something else, and now they're not. So I noticed some of these were twisting, and the worry was that you could then, the way that the deck is constructed, that some of that could fall down. So we installed some scaffolding along the ship, which is still there now, because when you're drying, you know that you are going to get some movement, and as it continues to dry, you will still get movement. What you don't want to do is try and hold it in one position, because if it wants to move, it will move. And if it doesn't move where you fixed it, it will move somewhere else down the line. We can see that from some of the fixtures that were put on. They were absolutely necessary, but some of the fixtures that were put on for the raising, you'll see that then further down the timber, it might have split somewhere else because it didn't want to be held there. So this scaffolding has gone in just to give us the peace of mind these bits are being supported. And then meanwhile, we have work going on to understand how the ship has moved. So long term, we'll be able to come up with a better and more aesthetically pleasing support system. So to help us with this, we have the kind of single points that we can look around the ship. We've also managed to get some full laser scans of the hull. This has not totally by chance, but it's more that opportunities have come our way that we've then taken. So some of the scans were done specifically. So for example, with the modelling of the airflow around the hull, a laser scan was done. We also then have been lucky enough to get some scans done by BAE, who are on the dockyard, and they actually used it as part of their training program for some of their students. So they came and scanned the ship. It's quite complicated because obviously it's not a whole ship and there's scaffolding and all kinds of bits and pieces, but it meant that we got free laser scans, which was great. And then we're doing work now to try and understand those. They've been taken at different points in time, which we can actually correlate to the two different types of peg that were sprayed, and also when we were drying, when all those ducts were there, and now drying without. And I think we do actually have another couple to add to that. There was one done not so long ago, which was actually for an interpretation thing. So being able to make a 3D model of the hull, but obviously if I get the data, I can use it for this purpose too. And you can do all kinds of stuff with this data then. This is just a very small example of showing a cross section of the hull and how you can zoom on into particular elements. So this is looking straight onto a deck beam. So you can see when it was being sprayed with peg that that deck beam is very square and very straight. And then I mentioned before the twisting. So this kind of shows you it through the data. And also that deformation at the top is because there's a crack that's formed on the top of there. So we have a project running at the moment, really looking into all of that data, which I think will go on for years, to be honest, because there's so much there that could be used not only for the kind of long-term stability of the ship, but understanding the conservation, and then also even interpretation, because you do get an incredible amount of detail with it. And so that's kind of more the mechanical, physical side of the wood. The project that I first got involved with was looking at the chemical state of the wood. The best way to think about this is that the whole collection has been marinating in seawater for 400 years. So there is all kinds of stuff in there that you wouldn't normally find in there, or you wouldn't find to that extent. You also have the things like iron. If they did corrode, they will have seeped into any kind of porous material near them. So things like the wood. So this is quite common in our collection that you see these are sulfate salts that form on the wood. This is a chest panel. The image on the right is where a iron bolt was in a gun carriage. So you can see that it's just completely corroded. It reacts with sulfur in the wood that's abundantly available in it from sulfur and seawater that's going to the wood, and you form all these sulfate salts, which don't look very good and are very acidic, and they can essentially just eat away the cellulose in the wood. So one of the things that we've been doing is, as we started to dry the ship, that's great for getting the water out, not so great for then transforming elements that are in the wood, which can then eventually form these nasty products. So some of the things we've done to try and look at this is an experiment we did at the European synchrotron in Grenoble. So this is some tomography on a piece of wood. This, first of all, was just looking at the wood and the wood, looking at everything that was there. So a kind of straightforward CT scan, looking at 2 millimeters from the surface and then within the wood. What you can see from here is you see at the surface it's really disordered. You don't really see any of the wood structure. And then as you go into the wood, you start to retain, you start to reintroduce some of the typical wood structure, the vessels and things like that you would see. What was great about this technique, though, was that at every point that you were collecting data, you could actually get almost like a chemical footprint of what was there. And then you can, if you know the kind of things that might be there, you can then match the different spectra that you get and then look at a distribution throughout the wood. So this was, again, was on a core sample taken from the wood. So the top is the surface, and then this is a cross section of a core going down into the wood. You can see the growth rings of the wood going down. So you can see actually that the core sample wasn't taken right on, right at the right angle. The one on the left is everything that's there. And then we have the peg. So you've got more peg at the surface. You've got more peg in the vessels and things like that. It's collecting where there is space. And then you find stuff like this. So this then we found where there's these tiny little particles in the middle. This then matched with a zinc blend particle. So this is zinc, iron, and sulfur. So we knew that iron and sulfur were going to be there, and now we know, oh, maybe zinc is something for us to look out for as well. And it raises all kinds of questions of why are they just there? Why are they not on the surface? Did they get washed out? It's so yeah, you get there's a lot going on in the wood. So just this is one of the core samples. So you can see from the surface into the interior. This is quite typical of how they look. this has been cut into sections. Where it's degraded, you can see that it's darker. And interestingly, this one, it's darker at the surface, and then it's got that patch that's darker in the middle. And we've ran various analysis on this. You can see at the surface, there is more sulfur, iron, and our friend zinc is there. And then again, when it's darker in the middle, you again get an increase in sulfur, iron, and zinc. And then the data below, that is actually a technique called FTIR, Fourier Transform Infrared Spectroscopy. Now, what this is really good at doing is determining or identifying those three major wood components I told you about at the beginning. Now, cellulose and hemicellulose preferentially degrade. So if you can pick those out against lignin, you start, as the wood degrades, you see much more lignin compared to the other two if you do a ratio. So where you have the higher points in that data, that shows that it's more degraded. So we start to build this picture of where it's darker, there's more sulfur, iron, and zinc, and the wood is more degraded. So there's still a lot more to do with that, but we know, and we know from other people that we've worked with, that this is something to be thinking about and to be prepared for, to do something about if it looks like it's going to be a problem. So a few of the different things we can do. You can try to remove things before you consolidate them, so before you do a peg treatment. This actually was after a peg treatment. So this is a gun carriage. If you've been to the museum, in the gallery that's opposite the ship, at some point in there is a cannon which has no carriage. And that's because it's this one. Because when I started at the museum, you can see here that this carriage is in a really bad state. It's covered in these iron and sulfur salts, those kind of grey salts. And they cause cracks and they're very acidic. So we pulled it from going on display, which was not a very popular decision, but we knew that it needed attention. And the problem with our galleries is, well, not the problem, but the thing that we need to be mindful with our galleries is, some of those artifacts are huge. They are not easy to take out. You know, it would be, we would shut down the museum, and that would be quite detrimental to us. So we made the case that this shouldn't go on display. So what we did was we did a treatment where we used an agent, a chelating agent, which preferentially removes the iron. So it takes that out of the equation, which we'd seen other people doing with some success. This, I think eventually it took out about 5 or 6 kilograms of iron. So it just gives you the kind of amount of iron that's there in it. So that goes into the solution, and you measure the solution and you can see how much has come out. Unfortunately, it also washed out some of the peg that we've done. So now we're having to do a peg treatment on that, and then we'll have to freeze dry it, and then eventually we'll get it back on display. So at some point when you visit in the future, you won't see a cannon without a carriage. It will all be complete there together. So that's one option for us, that you try and remove the problem before you start treating it and putting it on display. Unfortunately, we already have lots of things on display. So some of the other things we look at is different types of treatment. So one thing we often do is rather than go straight to working on the various materials, we'll simulate a particular problem. So for example, we'll take blocks of fresh iron and we'll soak them in iron sulfate solutions. So it's not Melrose wood, it's fresh wood, and then we'll try different experiments on them. This particular one was using a patch which has got a chemical in which will go and react with the iron and pull it out. And again, this is something that we're working on at the moment. We've had some success with it, but there's lots more that we'll need to do before we would roll it out. But what we're trying to do is arm ourselves with lots of different options. So if something's already been through a treatment, is it on display, we could potentially treat it in the showcase and not have to take it out and behind the scenes. So it's still there, and we can deal with the problem there and then. One of the other projects that I have been working on was trying to come up with a new material. And in this, we were looking at exploiting a few different material properties. So I'd worked, when I was at Kent, worked on developing some nanoparticle treatments, where the nanoparticles would go into the wood, react with some of the nasty stuff there. However, it remained in the wood, and that always made me think, that's not ideal. I don't really want to be putting more stuff in the wood. I want to be taking stuff out that shouldn't be there. So we started a project looking at making nanoparticles which were magnetic, and coating them with something which then had a receptor that would capture iron. And so the theory of it was that you would have these nanoparticles, you could drag them into the wood, they would do their thing, capture all the nasty stuff, and drag them out again. Now, the reason that I really liked this idea was it, like I say, that the whole collection, nearly all the collection has got something in it that shouldn't be there because it's been in the seawater for so long. So this technique, whilst we were applying it to the wood, theoretically could be then tailored to different elements, whatever was the issue with a particular material, as long as there was a pathway going into the wood. So yeah, this was a research project that I ran with the University of Sheffield, and we did get some results on a piece of Merrow's wood, but it is an incredible amount of work getting to the point of making these materials, and you have a very small amount. And they were able to successfully show that the nanoparticles went in, came out, and they had some iron, and so they captured some. And now what we need to do is then roll that out to a much bigger study of, do we get all of the particles out? How much iron does it remove? Are there any kind of deleterious effects on the wood? So that'll be the next place that we take that. But in principle, it's a really exciting idea. And so just to touch on these materials, with the wood, with the iron and sulfur that's forming in it, we're now seeing this forming in other materials as well, so such as bricks. We have a lot of bricks in our collection, which is quite surprising to some people, but it was used in the galley and also in ballast. And you can see here the salts forming. This here is a scanning electron microscopy image and then some elemental analysis of it. And what you can see is often you get these kind of plates of the salts forming, and rather than chemically degrading the material, often what happens here is it physically breaks it because the crystal forms. And what's particularly damaging or dangerous in this situation is that if you get high humidity and the salt dissolves, when it recrystallizes, it will get bigger and bigger and bigger, and then it can really damage the bricks. So we have just started recently a project with the University of Kent looking at really understanding what the salts are and how they're reacting to different conditions and how they are actually interacting with the brick material. But it just gives you another idea of some of the things that we're having to investigate. And then the last material I was going to talk about was our iron. So marine archaeological iron is notoriously difficult to conserve. It is a miracle that we have as much of it as we do. Again, this goes back to it being absolutely sealed in the sediments. We have over 1,200 iron cannonballs in our collection. They have all gone into passive storage. So this usually is just in an alkaline solution. So it very considerably slows down or even stops any corrosion from happening. And then some of them have been through various treatments to try and remove chloride. So it's the chloride in the salt in the seawater which is particularly damaging here. Or more, I should say, the combination of having chloride there, any kind of moisture and oxygen. This is like the perfect storm for iron, that you get a product or different products forming, in particular one called a kaganite, a corrosion product. And what can happen is you see here that there's cracks in the iron. You can get these cracks and then the corrosion starts forming inside, and the volume of the corrosion product is larger than the volume of the original metal matrix. So what happens is the pressure just grows and eventually it'll just crack off. So you see the image at the side that basically it's just completely cleaved off this part of the material. So that's quite a common way that they'll degrade. So we had a set of these that have gone through various different treatments and we put them on display in our museum. Now, the showcases in the museum are optimized for organic materials, and it meant that the humidity was just way too high. So we started to notice some of these cracks. So we took nearly all of them off display and started a research project looking into them. Now, unusually, we decided then to do some destructive testing because, as I explained, a lot of this is happening from the inside out. So it's very common then that you'll be, people say, right, well, let's take some samples from the surface. And whilst that's a good place to start, it's not really telling you everything that's happened. And I think one of the things that we're very fortunate with our collection is that we have a lot of repetition in there. And that's not to say that we will just experiment on anything. It has to be a very informed and considered decision. But the argument made in this case, or the argument that I made in this case, was we have all these cannonballs. Some of them haven't yet been conserved. We have the opportunity and the expertise and knowledge to do some experiments on them where it will inform not only our collection but other people's collections, because it's quite unusual to have this many, and this many that really, other than what we've done to them since they've been excavated, you would otherwise think that they're fairly uniform in terms of when they were made, when they were lost, when they were excavated. So we've done quite a lot of different experiments on these. This shows the student Haley slicing in and taking a segment of the iron. You can see at the bottom that once you, obviously it looks corroded on the outside, once you get inside, it is like shiny new metal on a lot of them. In reality, quite a lot of the ones that we tested, because they've gone through different treatments that hadn't fared very well, they were already in pieces. So whilst we did destructively test them, they were already fairly destroyed in terms of not being a whole cannonball anymore. And just to give you a flavour of some of the things we're able to do. So these are elemental maps, which then we can start to map where the chloride is within the material. So for some of the treatments, there wasn't any chloride on the surface, but there was in pockets inside. Other treatments, we found that there was chloride on the outside of the material, which was surprising because the treatment had been done to remove the chloride. So then we had to backtrack that and think, well, what caused that? What were the different steps in the treatment? Well, you know, potentially tap water was introduced at some point and that would have had chloride in, things like that. So we've got some really interesting results from that. And we've also, that's just jumping a little bit, I hope you can see that okay. We also, this is a very small bit of an iron cannonball that had broken off. And we were able to do some tomography on there. You can see how, so that's the surface, but then there is quite a lot of metal there. And again, it's inside. The darker areas are where the corrosion is. And that's just showing you all the way through. So you can see where the kind of darker corrosion areas are. And then from this, we can take it a step further and map the different parts of that. So we can look at everything that's there. We can look at which bit is just the metal. We can look at where the cracks are. We can look at where the corrosion is. And then we can start to see which bits coincide together. So we've just finished one PhD student has just finished and another has started. There's an enormous amount. So here is one of these things where you start doing one thing and go, it's very easy to go down a rabbit hole and look at lots of other stuff. But some really interesting results already that inform us of how previous conservation treatments have worked, and identified some that maybe we wouldn't want to do again or would want to alter. So I was just going to finish off actually with talking about a couple of other objects and just some of the challenges of dealing with them. We have such a range of objects and the type of conservation that is required. So it can range from, you know, something very small like a gold coin or a leather hook sleeve, and it's very fine and the conservation of it is very detailed, or like something that's broken and has to be put back together, and the kind of artistic skill that goes into doing that is phenomenal. But then it ranges up to kind of more industrial conservation, so with huge timbers, tanks, some of the images you saw before. This here, I'm showing the stem post and the pump. So the stem post was raised, the pump was raised back in the 80s, that's on the left. The stem post was actually raised in the early 2000s. This was the MOD were going to dredge over the site, so they sponsored some excavations. So there was a whole load of stuff that was raised then. In fact, they were the last things that were raised from the seabed between 2003 and 2005. So that shows it being excavated. And then these were both in treatment when I first started at the Mayo, so in a peg treatment. And because there was no plans for them to go into the museum at that point, they were safe there, so they kind of were left there to keep ongoing with the peg treatment. And then once the museum was done and we'd got through all these different phases, we were like, right, what are we going to do with those? Because they're huge. So the pump is like 8 or I'm losing my memory now, 10 meters long. It's very long. And the freeze dryer that we have is only 6 meters long. So we had the options of cutting it in half, which nobody felt very comfortable with, sending it to another freeze dryer, which would involve going to another country and paying tens of thousands of pounds, which just made it not really an option. And then the other idea we came up with was to do the peg treatment such that we could put it into the ship hull and let it dry alongside the ship. Now, there were some differences in there because the tubes weren't around the ship anymore. It wasn't drying exactly the same. But on balance, we decided this was the best option. And from there, we then had to navigate getting it from our conservation facility, which is in a different building on the naval base, into the museum. Now, if you remember, the museum is built over the dock. At one end, there is actually a hatch that opens, but that again is only about 6 or 7 meters wide. So just was going to finish with a few time lapses showing you the kind of work involved getting these items in and out. So this is getting the stem post ready. It's also got a very non-uniform load distribution. So getting the lifting equipment right. It also does, this one have a joint, but not one that came apart, but enough that we were kind of slightly concerned about it. You'll see the team now positioning it. This was the day before we moved them to the museum. So we got everything in place by the doors, ready for them to go out. This is also a massively awkward shape, you can see. So lots of foam there. So that was day one. This was then up at the museum. The lifting team, I really felt for them because they, in fact, one of them said to me at one point, how much is this worth? And I was like, it's really best not to think about that. So the best way for you to think about it is this is a massive piece of timber and we need to get it into here safely. So yeah, they had some fun and games getting it right. You can see at the top there, at this particular point in time, the wind decided to pick up and I thought I was going to have a heart attack. And then you can see where the hatch is open. At some point, the view will change over to there. And we were stood there watching this go in. We did all this quite early in the morning as well. That's always my preference, to do these things definitely before the public are there, but also actually before a lot of staff are on site too. Otherwise, everybody can't resist looking. I would be the same. But yeah, you can see it was really challenging to get it in there. And there was even a point where he was like, well, I think we're going to have to lift it back out. And I was like, that's me stood there. And he said, oh, I think we might need to lift it back out. And I was like, I really don't think we should. I think that needs to go in now. And eventually it did, with a lot of maneuvering. So that's quite a drop down. And then the team were ready with the rollers down there for them, the trolleys for it to be lowered onto. But you can see it was quite a tight fit. So then it went into the dock, and then the next morning, that's jumping a bit, we had the joy of getting it into the ship hall, which were even smaller doors. Yeah, I'll see if I can move that along at all. I might have to give up on that one. Oh, let me see if I can just get it to, you'll see it coming in. Maybe if I do it like that, you'll see. And then this is where it's been positioned, which is where it would have been. And once it's dried, what we'll do is it essentially needs to be rotated 90 degrees, and it's that part of the ship there. So that's the plan eventually. Once we're happy that it's dried out and we've stabilized it, that we will need to design some kind of mount that fully supports it, but also enabling the public to be able to see it. And I think that, yeah, that's the end of it in there. So yeah, like I said, we worked with lots of different people. Oh, I can't get that to move on now. Oh no,